to introduce Tom Henzinger as our keynote speaker. So Tom is the director of, the president of IST Austria, the institute that has been created about 12 years ago, but that is already, according to many parameters, doing being more successful than many universities with century-old, which are there for several centuries, and it is Tom is very well known in our community. It would be very long just to mention all the things that he achieved, but let me just mention all the seminal and influential work in hybrid and time systems, in interface theory, software model checking, just to mention a few. And these days, one of the topics that Tom is passionate about is runtime verification. So today, Tom will tell us about his recent work on the role of the assumptions in runtime verification. So Tom, please.
Dan, thank you. Thank you very much for the introduction. Thank you, all of you, for the invitation. Very happy to be here, unfortunately only virtually. There's a small paper in the proceedings which corresponds to the first part of this talk, and this is jointly with my student, Ege Sarak. Just to set the stage, this is the setting in which I'm considering the runtime verification or the monitoring problem. So a monitor is watching a system. Actually, the system is black box. The only thing the monitor sees is the inputs and outputs to the system. And the monitor produces a verdict while watching the system. So it also produces an output stream. And I should say also, this is an online setting. We've actually constrained ourselves to the monitor having a bounded number of operations per system operation. That's actually an interesting model of computation that goes back to the early 60s and Michael Rabin and others. And at that time, this was called real-time computing. And so they really looked at various automata models with this constraint. And some of this actually has proven useful in our work. So I said this small paper is only really the first part of this talk. I'll also want to give you a taste on some other things I've been doing in monitoring recently. Particularly, I'll talk a bit about register monitors. This is work with Thomas Ferrer and Ege Sarak, on limit monitoring with Thomas and Bernhard Kragel, and on quantitative monitoring with Krishnendu Chatterjee and Jan Ottrup. So the advantage of this is actually I can wake you up 3 times during the talk because it will sort of restart, and these are really 4 rather independent modules, but they're also linked by assumptions, the main topic of the talk. So Dan has already said, and I guess he knows because we talk regularly. I've become actually, even though I'm not a regular at this conference, or not yet, I've actually become quite interested in runtime verification. And I think there are 2 mega trends in computing that actually will make runtime verification extremely important over time. And these 2 mega trends are, everywhere we see that hardware parallelism increases, right? This is Moore's law goes now into more cores per processor rather than faster processors. We see data centers, computer clusters, and so on. So we have enormous amounts of parallelism, and it's hard to program parallel programs. So it's actually hard to get maximal performance out of this. So I'm quite sure this increasing amount of parallelism, actually, some of it will go into things that are not just sort of increased performance, that are used for things like increased assurance, correctness, other robustness, checking other properties on the go, online. So I can see a world where there is on any many core processor, some cores compute, other cores check. The same about computer clusters. And that's, of course, that is exactly runtime verification. And the second mega trend, I think, is software is obviously becoming increasingly complex, namely in ways that is very hard to deal with static formal methods, right? Software increasingly contains things like neural networks, calls to the cloud, library components. So the static, what I call verification gap, the gap between real systems and what's statically verifiable, is actually increasing. We're not really catching up there, and it's likely to increase even more if we think about that. If AI plays a bigger and bigger role and so on. So again, this is a unique opportunity for runtime verification. So with this sort of prediction, I have sort of two observations on runtime verification that I think, at least I find personally important. One is, while static verification is technically, in an automata theoretic setting about an emptiness question, runtime verification is obviously about a membership question. Is a particular behavior, does it satisfy a specification, versus emptiness asks, do all behaviors satisfy a specification? And so I think this should have some ramifications, in particular that formalisms and methods that have been developed for static verification, is from temporal logics to other formalisms, are not necessarily at least it's not a priori clear that they are the best formalisms for runtime verification. And secondly, I think there's an enormous opportunity for more quantitative and approximate methods. I mean, quantitative and approximate methods are hard to deal with in static verification. What does it mean for a system to be almost correct? It's simply difficult to approximate systems. But if you look at individual behaviors, this is much easier to do. It's very easy to say that the behavior is almost correct. You just need a distance between two behaviors rather than a distance between two systems. So this is one point. And the second point is that I think for really widespread runtime verification, and that really should be the vision, I think, really widespread monitoring to be accepted and to be trusted, I think monitors need to be third party. That means they cannot be built by the same people or vendors that actually built the software that's being monitored, because otherwise, then you have a trust problem. I think they need to be unintrusive. So that means the overhead, obviously, for monitoring needs to be extremely low. Otherwise, it's going to be not widely accepted. And it also means basically, actually, both third party and unintrusive also means that monitors more or less have to be black box. That they have to look at the system as a black box. And thirdly, I think they need to be online because we want monitors to immediately give warning signals. So monitors really are real-time systems, and they're also best effort systems. It's perfectly okay if a monitor misses something or doesn't give, isn't complete in a sense for uncovering certain errors on behaviors, but it needs to make the best possible effort that's possible to be made in real time. That's the setting in which the rest of the talk, which is more technical, it really limits itself to. So let me start with a very simple property. So I have an alphabet of observations. This case is A, B, T. T stands actually for tick. It's a clock tick, if you wish, and O stands for other. And I'm interested, so a behavior is an infinite word over these 4 letters. I'm interested in the response property, a very classical liveness property, right? That every A is eventually followed by B. And write it here down in temporal logic. So we have this long, infinite, really, sequence of letters. And you can see there are many O's and many T's with clock ticks in there. And there are occasionally there's an A and there's a B that follows the A. There's another 2 A's and there's a B that follows the 2 A's. And we want to make sure that the response property just says that every A should eventually be followed by B. Now, this is what's called a liveness property, because every finite prefix, no matter what it is, no matter how long it is, can be extended to actually an infinite word that satisfies the property, right? You just have to add a B and only O's. Then you know that every A is followed by a B. It's also a co-liveness property. That means a complement of a liveness property, because every finite prefix can also be extended to an infinite word that does not satisfy the property. How do you do that? Well, take any finite prefix and add only A's, right? Have an infinite suffix of A's and the property is violated because those A's are never followed by B. So this property is live and co-live, and these are the worst properties for monitoring. I mean, they're not monitorable in any sense of the word because no finite prefix tells you any useful information about whether the property is satisfied or violated. So a monitor can do nothing useful here. Technically, we say no finite behavior allows a positive or a negative verdict by a monitor. And a monitor will give a positive verdict if all infinite extensions satisfy a property, and it will give a negative verdict if all infinite extensions violate the property. So let's look at a different version of this property, which we call bounded response, where every A is now followed by a B, but not eventually, but within 5 clock ticks. So there can only be maximum of 5 T's between the A and the subsequent B. Okay, you can see that this long word I wrote down here violates this property because this second A here, there are more than 5 ticks. Yeah, there's 7 ticks or something until the B happens. So it violates the property. So bounded response is actually not live, right? And it's not live because if a word starts with A and then there's 6 T's, it's already violated. So not every prefix can be extended to a satisfying word, and that for monitoring that's good because that means if the monitor sees an A followed by 6 T's, the monitor can actually give a verdict, namely violation of the property, a negative verdict. Bounded response is also not a safety property. A safety property is one where any violation, if you have any violating word, a monitor can give after some finite prefix a negative verdict. So every violating word has some finite prefix such that all extensions of that word actually violate the property. And this is not the case here for bounded response because consider the word which starts with A and then has only O's, infinitely many O's. That violates, right? Because the A is not followed by a B. But there is no finite prefix. The monitor cannot say after 10, nor after 100, nor after 1,000,000 O's that the property is violated, right? So it's not safe, it's not live. It happens to be actually, it's co-live, its complement is live because any finite word you can extend with A followed by 6 T's and you get a violation. So any finite word can yield a violating word. Any finite prefix can yield a violating word. So in the Pnueli-Sachs definition of monitorability, and that's the one we're going to use, bounded response is monitorable exactly for that reason. And what I'll now do is I introduce assumptions to the monitoring problem. And the assumption is useful actually in general for real-time properties like bounded response, is that there are infinitely many clock ticks. Time diverges. So the universe of behaviors is limited to those behaviors that contain infinitely many ticks. In temporal logic, you write this box diamond T. That's now our assumption. And under such assumptions, things change. It has been known for a long time, almost 30 years now, that actually bounded response is safe under this assumption. What does it mean? If you take an infinite violating behavior, so that behavior has to have infinitely many ticks, but it's violating, that means there's an A that's not followed by a B within 5 ticks. But if a behavior contains infinitely many ticks, then there must be a prefix that already violates it, namely the prefix where you take the first 6 ticks after the A. That's a violating prefix. So assumptions can make a property that's not safe and can turn it into a safety, or what we called 30 years ago a relative safety property. And the whole idea behind the small paper that you find in the proceedings is that assumptions can make properties not only safer, they can also make them more monitorable. And let's try to formalize this. So what's an assumption? An assumption is simply like a property is an infinite set of is a set of infinite behaviors, and it restricts the set of all behaviors that we look at. Where can assumptions come from? Assumptions can come from a variety of different sources. They can come from knowledge about the system under scrutiny, right? If I know certain things about the system, so I give up here this black box. If I somehow know something about the system, that's of course can enter as an assumption. But it doesn't have to come from the system. This assumption that there are infinitely many clock ticks has nothing to do with the system. It's a physical assumption about the world, right? It can come from other sources. And it could come in particularly by decomposing a monitor, having, for example, monitoring a complicated property, decomposing it into 2 monitors that monitor simpler properties each, where each monitor uses the verdict of the other property as an assumption. I will not go into this. I think this is work that needs to be done. One can think of even circular assumptions in this context as in assume guarantee reasoning. I don't think that I haven't found anything on this, but I think this is a really interesting direction to pursue. So what is now the definition of monitorability under assumptions? And it's very similar to classical Pinelli-Sachs monitorability. We just add now the assumption as at every place where a finite or an infinite word is chosen, it's chosen from the assumption rather than from the universe of all possible worlds in sigma omega. So we say a finite behavior alpha allows a verdict under so a positive verdict under assumption A if all extensions of alpha in A, so not all extensions, but all extensions of alpha that are in A satisfy the property, and it allows a negative verdict if all extensions in A violate the property. So if I know that my infinite word will come from A, after alpha, I can say the property is satisfied or it's violated, under the assumption that the infinite word will be in A. And then the property P is monitorable under that assumption A, if for every finite prefix in A, there is some finite continuation beta, such that after that beta also has to come from the assumption A, of course, such that after alpha and beta, we can give a positive or a negative verdict. So for every finite prefix, there's the chance that at some later time, there will be a verdict. If you put in sigma omega for A in these definitions, you get exactly, of course, Pinelli-Sachs monitorability. So I gave you one example with the infinitely many clock ticks. Here's another example of an assumption. I've now my response property. The response is A is always eventually followed by B. And this was not monitorable. Here's an assumption that makes it monitorable. That assumption says whenever you see, whenever an A is followed by another A without an intervening B, then actually you know that there will never be a B. Okay, that's the assumption. It's written here. Maybe go through it a bit in temporal logic with the past operator. It says whenever you see an A and there hasn't been a B since the last A, so that means there are really two A's without a B in between, then there will never be a B. Now, under this assumption, so that in other words, the assumption also, you could view it also as sort of the safety part of A's and B's alternate, right? So the proper response becomes monitorable. Why? Because if you take any finite behavior and extend it with two A's, under this assumption, you know there will never be a B, so you can immediately give a negative verdict. So now what was a rather simple example, what is monitorable under assumptions in general? And here one can actually redo much of the theory of monitorability for assumptions. It's not even terribly difficult to redo it. So let me do what I consider here to mention just the most important results here. You'll find more in the paper. You know, first of all, let me say a property is safe under an assumption if for every behavior that's in the assumption but not in the property has a finite prefix that allows a negative verdict. And its property is co-safe under an assumption if for every behavior that's in the assumption and satisfies the property has a finite prefix that allows a positive verdict, right? These are the two obvious definitions of adjusting safety and co-safety to assumptions. Now we can call for any assumption A, we can call the obligation properties of A relative to A to be all positive Boolean combinations of safety and co-safety under assumptions. And let's call the monitorable properties relative to A all the properties that are monitorable under the assumption A. And then you can show, similar to the theory without assumptions, you can show for every assumption A, the obligation properties relative to A are all monitorable, but is actually a strict subset of what's monitorable. And the monitorable properties under assumption A are closed under all Boolean operations. To go one step further, I think it's very intriguing now to take the topological view of infinite behaviors. So that's the so-called Cantor topology, which is the topology of the metric that makes two infinite words close if they have long common prefixes. So the longer the common prefix, the closer to infinite words. So the topology that's induced by that metric has the following well-known properties. And this goes back to Alpan and Schneider, and for monitorability, the result is by Volker Dickert and Martin Leuker. It says, the safety properties are exactly the closed set in the Cantor topology. The co-safety properties, by definition, therefore, are immediately the open sets. The live properties are exactly the dense sets. And what Dickert and Leuker showed that the monitorable properties, the Pinelli-Sachs monitorable properties, are exactly those sets where the boundary of the set has an empty interior. So that's a purely topological characterization. If you carry this over now to assumptions, under an assumption you get a topological subspace of the whole space. And again, many of these results carry over. Just if we look at safety and co-safety property relative to an assumption, you have the very interesting result that for every property P, there's a unique weakest liveness assumption A that makes P safe relative to A. And there's a unique weakest liveness assumption B that makes P co-safe under B. And you, of course, are generally interested in assumptions that are as weak as possible, right? Because the weaker an assumption, the less you assume. The proof is purely topological, and it's a well-known construction that, for example, that particular A here you construct as the complement of the closure of P minus P, and the particular B you can construct as the complement of P minus the interior of P. Both are liveness properties, and actually they are the largest possible liveness properties that make the assumption safe and co-safe. Now, what about monitorability? And there we have a result, but it's not as pleasing, and I wonder whether there isn't a stronger result. Anyway, the result we have is that we can make every property P monitorable by introducing the right assumption. And we can, in particular, we can always introduce a co-safety assumption C such that P becomes monitorable under C. And again, it's a purely topological operation where, you know, the boundary of a property P is well defined. It's the union of these two sets, the closure of P minus P and the P minus the interior of P. And then C can be constructed as take the boundary, then take the interior. Since we know that the property is since P is non-monitorable, right? The boundary becomes non-empty, and so I take the interior of the boundary is non-empty, and then I take the closure of the interior of the boundary and the complement of that. I can show this is always a co-safety assumption, and it makes actually P monitorable. So to do this on an example, you know, the property we have is now a more complicated property. Its response, every A is followed by B, or there's an A that's not preceded by B's, and the holding end together with eventually you see a C. Can think of the C as a reboot or something. Now, that property is not monitorable. Why is it not monitorable? If you simply see an initial B, that B has no extension that either where you can say you can have a positive or a negative verdict. Why? Because it's initially B, so this second disjunct is violated. That means you really have to see every A followed by a B, and you have to see eventually a C. No matter what extension you see, you cannot have both satisfied or violated, because the only thing you could see the C satisfied by having eventually a C, but you'd still be missing. You still, you know, the response could be still violated here. But under that assumption, if that second disjunct is actually true by assumption, then suddenly the property becomes monitorable, and that's actually exactly the assumption, the co-safety assumption that the previous theorem gave us. I have to admit the example is it's not something where I can give a very natural interpretation to that theorem. What is the assumption that's being constructed? And in fact, the structure of the assumptions that make a property monitorable are, I think, are not quite clear to us. And that's, in fact, I would call this a big open question here, is if you're given a property P, so we know there are assumptions that make that property monitorable, but generally there's no weakest such assumption. So it would be interesting to know what is the structure of such assumptions, at least for certain classes of properties, if not for all properties. But as far as I know, there's no good answer yet to that. So there's work to be done. Let me conclude this part on assumptions by saying one thing, because I think that's also important. This whole, everything I said so far was talking about very arbitrary properties and assumptions. So any subsets of sigma omega. Of course, you could limit yourself to universes that are smaller, for example, the omega regular properties and assumptions, those that can be defined by automata. You can limit yourself even further by only talking about what's called the counter-free omega regular languages, namely exactly those properties and assumptions that can be specified in linear temporal logic. Actually, all the results I gave so far apply equally in all three cases. So you can do all, for example, also all the topological constructions if you restrict yourself to omega regular properties or to LTL properties. So now here's the first reset. And I will now talk about monitoring with registers. And this actually fits in very nicely with assumptions, because it shows you, what I've shown you so far is that assumptions can make non-monitorable properties monitorable. Assumptions can also make a monitor save resources. If you have a property that already can be monitored with a certain number of registers, under the right assumption, you can actually monitor the property with fewer registers. I'll be very brief here, and if you're interested in a paper, this appeared at LIX 2 years ago. So here's a safety monitor with registers, in particular with counter registers, where the only thing I can do with counter registers is increment and check for equality. Equivalently, you could increment and decrement and check for 0. So the language, this counter safety monitor, and it's called a safety monitor because it defines a safety property, it is that, you know, you have A's and B's, and in every prefix every prefix, no matter how long or short, should contain more A's than B's. Okay. How do you do this? Well, if you have counters, you simply count the A's and B's. There's no big magic here. The counter X counts the A's, the counter B counts the B's, and the only condition is that you know, in the state on the left, you have an equal number of A's and B's. In the state on the right, you have more as A's than B's. So if you see another B and you still have more A's than B's, if y plus 1 is still less than X, then you stay in the state of the right, on the right. But if you now, the next B makes it equal, so if y plus 1 is equal to X, you go to the state of the left, and you have in equal numbers of A's and B's. And then there's no transition out of the left state on a B, because that would violate the property, right? That would mean if you have an equal number of A's and B's, and if you see another B, you would violate the property. So this safety monitor simply means it's an automaton, in this case, an automaton with registers with no acceptance condition, but it's not complete. There's certain states, you know, certain transitions are not enabled. For example, there's no B transition enabled out of the left state. And if that's observed, that's a violation. So now, if you now enlarge the alphabet, and you have, instead of just A's and B's, you have K plus 1 letters, namely 0, 1, 2, 3, up to K. Then the generalized property PK says simply, you know, the number of K's in every prefix, the number of K's is more than the number of K minus 1s. The number of 7s is more than the number of 6s. The number of 6s is more than the number of 5s. The number of 3s is more than the number of 2s. The number of 1s is more than the number of 0s. That's my property pk, up to the number k. Now, we have shown that to monitor this property with counter registers, you actually need k+1 counters. I mean, it's obvious how to do it with k+1 counters. You count each letter with a separate counter. But what we proved is that you cannot do it with fewer counters. And you cannot do it with fewer counters in real time with a bounded number of operations per input letter. Now, this is interesting, of course, because it gives you immediately an infinite monitor hierarchy that languages, what can be monitored with counters gives you an infinite hierarchy. Every extra counter register gives a monitor extra power. And then you can ask, what if you don't have just counters? If you have, for example, registers you can add. So if you can add and subtract, you can actually simulate any number of counters in real time with 4 registers. So, in other words, you might need a large number of counter registers. You could do it with 4 add registers. But what we don't know actually, and there's an open problem here, is if you just look at the adder hierarchy, we don't know if it's strict or not, if it collapses or not. I don't know, for example, if k+1 add registers are more powerful than k add registers. Same is actually true for multiply registers. We don't know. The best we can say is if we have some very powerful operations like exponentiation and factorization, then we can actually simulate any number of registers in real time by a single register. So this gives you an expressiveness hierarchy. Now, how does this relate to assumptions? Well, if we just take the language we had, that for all the letters 0 up to k, there are more k's than there are k-1s and so on, I can split the requirements in the middle and look at the letters from 0 to I and at the letters from I+1 to k. And I can make an assumption about the letters from I+1 to k. And under that assumption, I need only I registers, I counter registers to check my property. So if I have such an assumption, I can obviously reduce the number of counters that I need to monitor a property. In fact, this can be the basis for a nice decomposition method for monitors. I could monitor the assumptions with k-1 counter and then use the k-I counters and then use the remaining I counters to monitor the property under that assumption. I also want to say one important word is there are still properties that are outside all registers monitors. For example, this property looks extremely interesting and natural for example, from a security perspective. You simply have, a sequence of finite words that are separated by some separator. I use the number symbol here. So if an infinite sequence of these finite words separated by the number sequence, and the property you want to monitor is that no word repeats. So for all I and for all j, alpha I is different from alpha j. That, for example, if you want to say that the nonce, security nonce is fresh, then it's exactly this kind of property. And what we showed is actually that this property cannot be real-time monitored by any number of registers, even if you have addition and multiplication. Okay, next quick reset. I want to tell you a bit about probabilistic assumptions. And that's work that appeared this year at CSL. So first, I have to make a small adjustment from what we so far considered only Boolean safety properties. I now talk about quantitative safety properties where the value set is not just yes or no, a property is satisfied or violated, it's actually some arbitrary value set, lambda. So every finite word has a value in lambda. That's a quantitative property. Now, real-time monitors, as we have seen them so far, or online monitors, monitor the past. They are deterministic automatas M with some verdict function which maps every state, for example, the automaton state plus the register values, to some verdict in lambda such that after every finite prefix, after the automaton reads that finite prefix, the verdict is exactly the function, the property f applied to that prefix. That's what a real-time monitor is, and it's simply a verdict on the past. Now, if you have certain assumptions, you can even make predictions about the future. And here's an interesting kind of assumption. Suppose your behaviors, your infinite behaviors, are generated by some random process, and that property f converges to a value over that random process. That means for all words generated by that random, if a word is generated by that random process, the f applied to all the prefixes of a word, that sequence has a limit, and the probability that that limit is the value lambda is actually 1. So that's my assumption. Under that assumption, and I'll give you an intuition of some concrete setting in a second, you can actually what we call limit monitor. So you can have a limit monitor is a deterministic automaton with a verdict function as before, which looks at the past but makes a prediction about the future, and it doesn't have to make a prediction immediately, right? Because it makes a prediction about the infinite limit in the future. So the only thing I have to require is that the verdict function of the monitor and the property f that is being monitored converge to the same value. Okay, let's make this concrete. The property I want to monitor is the mode of a sequence. So if I find an alphabet of letters, in any finite prefix, some letter occurs more than the other letters. Ignore equalities for the moment. This is simply a definitional detail. So that's the mode of a finite sequence. And if my infinite words are generated by a finite connected Markov chain, then actually the mode, this mode function converges. I want to build a monitor that predicts what the mode is. So first, let's look at real-time monitoring. To have a real-time monitor which tells me what's the mode of the past, the finite prefix I saw in the past, I require as many counters as there are letters, right? This is similar to the previous problem I have. There's simply no way, if I have k letters, to do with k-1 counters to determine which is the letter that occurs most often, to determine it in an online real-time fashion. So real-time monitoring the mode requires a number of letters, many counters. Predicting actually the limit of the mode over the infinite word can be done surprisingly with 4 counters. How can that be? Well, here's the algorithm. I wrote it here down in words. I hope it's easier than in pseudocode, but the basic idea is the following. This is the monitoring algorithm. So we partition the infinite word into segments, alpha 0, alpha 1, alpha 2, alpha 3, and so on, of increasing length. So alpha 1 is longer than alpha 0, alpha 2 is longer than alpha 1, and so on. And I'm actually computing the mode of each one of these finite segments. And since the segments become longer and longer, the limit of this sequence of modes is actually the mode of the infinite sequence, under the probabilistic assumption that this whole sequence is generated by a Markov chain. So what do I need to do? I need to have simply for each alpha, I have to maintain a hypothesis of the mode, call it MI. And then I cycle round robin through all the letters in sigma, looking at the first letter, at the second letter, at the third letter, and so on. And then when I'm done, I'm looking again at the first letter. So, and if the letter I'm looking at occurs in my sequence, alpha I, more often than my current hypothesis, what the mode is, then I change that hypothesis to that letter that occurs more often. Otherwise, I keep the hypothesis. And one can show that this monitoring algorithm actually converges to the mode. It actually involves quite a bit of heavy math to show this, but the algorithm itself is very simple and intuitive, and I think that's a fascinating topic, actually. Last topic, and maybe even quicker than the others, looking at time. Now, monitoring really quantitative properties. And by really quantitative, I mean now the mode was already a quantitative property. By really quantitative, I mean something like maximal or average response time, which is a number. And since it's a number, you can approximate it. So first of all, I give you a monitor here, a counter monitor for monitoring response. I think I can skip. Well, let me actually quickly go through it. So that we have the original alphabet A, B's, T's, and O's, and bounded response. We want every A to follow within 5 ticks by a B. Well, we just count the number of ticks with some register X, and see if we see a 6th tick, then there's no transition out of this state, and therefore there's a violation of the property. So you can write such a monitor also with something which we call a nested automaton. Nested automata are actually quite related to the temporal testers of Pinelli and Sachs, and they are a limited form of alternating automata. The idea is that an automaton can spawn off other automata. In this case, we want to have, whenever we see an we spawn off another automaton, that automaton called K. That automaton simply counts the number of ticks until the next B. And we do this for every A. Okay? So this is a more compositional way of constructing a monitor for bounded response. Now, if bounded response is still a qualitative property, we can make it quantitative, for example, by looking at maximal response. And a maximal response monitor should give for it, after every prefix the maximal response time so far. That means the maximal number of ticks between an A and the subsequent B so far. So I need the X to count the number of ticks between an A and a B. And I need a verdict, a register here, which is updated whenever the number of ticks is larger than the maximum so far. Okay, so this would be a monitor for maximal response time. It now is really a truly quantitative monitor in computing the maximal response time. You can do this also in this decomposed fashion by simply having, you know, a simple monitor for each A, count the number of ticks to the next B, and then have in the master, so to say, which spawns off the other automaton to have every K to keep the maximum of these so far. Now it becomes interesting if we go from instead of maximal response time, we want average response time. Why? Because I go back here to maximal response time. Because in maximal response time, if we see an A, we can ignore all the other A's until we see a B. Why? Because the number of ticks between the first A and the subsequent B is going to be larger than the number of ticks between any subsequent A and the same B. So we can ignore all of them. For average response time, we cannot ignore these A's. And this is what makes the problem more difficult. So average response time, actually, you need, if you do it, you cannot do it with counters. You need to have true addition. I mean, for you count the number of A's, and for each A, you can compute the number of A's before the next B. And then whenever the number of, ever see a tick, you don't increment, but you increase it by the number of A's you have seen so far that still wait for a B, because each one of them adds into computing the average response time. And the verdict function is simply then, you know, dividing this total sum X by K, the number of B's. if you do this with this dynamic creation of nested automata, actually it's more elegant and simpler to see it. You simply have count again for each A, you count the number of ticks until the B, and you just keep adding here in the master automaton. You keep always adding the value that comes back by this spawn-off automata. So in a sense, what you technically is you compute the mean payoff, means the average of the verdicts generated by counter automata, and one could actually show that not only can you do monitoring, online monitoring that way, you could actually do even static verification that way. That was in a paper we presented at SAS a couple of years ago. For the point of this talk, I should stop, and I'll stop with this is really the last technical slide, and this is really looking forward here. And say I showed you now quantitative properties in very discrete model of time, where t was simply number of ticks. At time was simply number of clock ticks. Of course, one can go to timed and hybrid systems here and then talk about signals. There's a very nice, for example, average response time is a signal, right? You have if a request and then you have the grant 2 time units later, then the average response time signal would go up from 0 to 2. Then you have another request with a grant 1 time unit later, then it would drop and it goes to 1.2, which is the average response time so far. So you can really imagine here you have continuous signals, and then you can start comparing monitors according to precision, because if you have now such an average response time verdict, you can over approximate it, you can under approximate it, you can certainly compare 2 monitor verdicts according to their precision. You can compare monitors according to the resource use, number of registers or other resources, number of clocks, for example. And you can compare them according to the strength of the assumptions they use. One monitor may use an assumption that, I don't know, that requests can never, if you have like the assumption we had before, that we have a request, there won't be another request until the next grant. With such an assumption, a monitor may be more precise or use fewer resources. So there's really a lot of theory to be done, and I really say to be done. I think nothing of this, to my knowledge, really has been done about monitoring. And let me end here. So I give you a little bit of taste. 4 topics. First, assumptions can make properties monitorable and save monitor resources. 2, the expressiveness of online monitors increases with the number of registers, strictly increases. 3, monitors can make limit predictions about the future for probabilistic processes. And 4, monitors can compute and ultimately also approximate performance measures such as response time. And I hope there's still time for a couple of questions.
Absolutely. So thank you very much, Tom, for this inspiring. Let us clap, virtual clap. And I would invite the audience to raise your hands. Okay, Wolfgang Arendt, I see that you want to ask a question. Can you please ask the question?
Yeah, hello, do you hear me?
Yes.
Yes.
Good. Thank you very much for this talk. This is Wolfgang Arendt from Chalmers University. I have a reflection on one of the points you made, which I find very inspiring, and that is that monitors can depend on each other or assume each other. And you mentioned the principle assumption guarantee, or sometimes also assumption commitment. And I think I understood from what you said that you didn't go further in this direction. I just want to share one reflection with you and the audience on this point, and that is that in all instances of this theory I have seen, the trick of two components or more components depending on each other's properties and be verified them statically or at runtime under the assumption of the respective other components. The trick to escape circularity there is always that you have a property which talks about the everything which happened so far, and you want to show that in your node, and you assume everything which happened so far minus one clock tick from everyone else.
Exactly.
This is how you escape the circularity. And obviously this can be done for safety properties, but from the gist of your talk, I get the feeling it could maybe be generalized also to some other, but certainly not all properties. It's just a reflection.
You're absolutely right. Yes, you need some sort of induction over time, and you said exactly how you do this. And yes, and as I said, I actually haven't gone at all in this direction. I hope some of you will.
Yeah. Thank you.
Thank you. So we have a couple of questions on Slack. I would like to invite Joshua Schneider to ask the question. Would you like to directly read your question? Otherwise,
yes, I can. Thank you. So I've been wondering in the limit monitoring example that you showed with the mode, it looks like your monitor that only uses 4 registers takes longer to converge than the natural approach where you have many registers, 1 for every symbol. So is this intuition true in general? Have you investigated this trade-off between convergence and the resource usage?
You're absolutely right. This is a very, very correct observation. Of course, yes. And no, we haven't. It's actually, rate of convergence is a very difficult topic here. And I must say, I'm also reaching quickly there always the limits of the math, I understand. But it's in general a difficult topic in ergodic theory. So it would be fascinating, of course. It would be another way to compare monitors, which one converges faster. And yeah, on the other hand, if you look at convergence rather than immediate real-time verdicts, you also get a lot of degrees of freedom. You can be slower. You can use basically an arbitrary amount of time to do work and produce, do computation to produce verdicts. And this also helps tremendously.
Okay, thank you.
Thank you. So I see that Joe also has a couple of questions on Slack. Joe, can you please ask them?
Yeah, thanks, Dan. Actually, one of my questions got answered in Slack itself, so I'll go on to the second one. So when you talk about monitorability here, it looks like there's an assumption that everything that you would want to monitor is fully observable. Is there some work on monitorability under partial observability?
Another terrific question, not in this context. No, at least not I'm aware of. So
I see that Ezio is here, and I'm aware of his work on monitoring under constrained resources. So when you need to drop certain events and you're not able to monitor them.
Yes, so it's a runtime verification with state estimation. So the idea is if you have if the monitor produces a lot of overhead, you may switch off the monitors and you may want to switch on later on. And then the problem is that you are missing some data, and then it's what is the probability that you are satisfying the property. If you know the hidden Markov models of the normal behavior of the system, for example, if you have learned like a behavior of the system when it's not observable, so then you can combine probabilistic model of your system with the observation that you have. So this is
So.
Let me just add this sort of type of best effort, and especially you're completely right. Partial information fits into this very well. I think is extremely attractive for monitoring.
So
especially, I think what would be interesting is to find connection with machine learning, where you have like this LTSM, this long time, always long memory, short time memory, and you know, how can you combine those with monitoring, for example? I mean,
thank you, Ezio. So we have one last quick question from Annie. Annie, please, you are muted.
Oh, I see. Sorry. Oh, hi. Oh, hi. Hi, Tom. Thank you for the interesting talk. I just have a quick question since you talk about work at several previous conferences. Are these implemented in, well, what are these implemented in, I guess? The tools or system you use or you build?
Well, I mean, to tell the truth, most of it is not implemented at all. It's theory, right? That you have a strict register hierarchy or so on. I mean, what a student has implemented is certain versions of the of these computing response times, which but none of them has really been targeted or is a robust implementation for monitoring.
Okay.
So view this at this point as theory, I think. Yes.
Well, very interesting theory. Actually, I have a short question. I mean, this is sort of obvious, but you mentioned that you know, when you talk about these properties, oh, these are purely topological properties, and right, usually that means those are invariants under some kind of homeomorphism. And so, what are, I mean, I don't know if there's something that's contrasting to it's, or just, you know, invariance. Of course, that's general. Are you contrasting there's some other properties that's not topological properties?
No, I'm not sure I understand the question. I think topology here has simply been a very, very, let me put it that way. There were actually originally in distributed computing, some people proved some results from scratch. For example, that every property can be defined as the conjunction of a safety and a liveness property and so on. And then only later it was realized that actually that's just an instance of a particular theorem that's known in topology and actually quite simple topological theorem. And so I find the connection extremely sort of intriguing because it gives a certain clarity of thought to the whole, to the definition. It also tells you that the definitions make some sense, right?
Okay, thank you. That makes sense.
So I would love to continue with the questions. Actually, I had a few questions myself, but unfortunately, we are out of time. So I would like to thank once again, Tom, for this really exciting talk. And
thank you.
And I would like to invite to the virtual stage now Dana Fiesman and Lu Feng, who will be the PC chairs of RV in 2021. So Dana, Lu, you are both co-hosts, and please share your screen and present what will happen next year.
Just a second, I'm trying to share the correct string. Okay, there he is. Okay, so hello everybody, and Dana, Lou is also here. Say hi. And so just wanted to tell you a little bit about the plans for RV next year. So the plan is to hold it in Los Angeles. This was the plans for this year, but coronavirus suggested otherwise. So we hope that next year we are going to be able to physically meet. If this is going to be the case, then so the plan is that when I will be the PC chair, as Joe is going to be the local chair. We are going to have it at the UC Hotel, which is right across the street of University of Southern California. The plan for the, in terms of the social event, is going to be in Santa Monica Pier, hopefully. In terms of the deadlines, they are going to be roughly the same as following the schedule that was in this year, but we haven't decided on the final dates. So you will get closer dates when we get closer to the area. And that's about it. I want to leave you some time to stretch before the next session. So we hope to see you all in LA next year.
Thank you, Dana. Thank you, Lou. And I think many of us will join, and I'm certainly hoping that we will meet each other physically in LA next year. So thanks again for the new chairs. And I invite you now to move to the other room for the continuation. We have today 2 more sessions, one on stream-based monitoring and the other one on temporal logic. And at 11 a.m. Pacific time, there will be also a business meeting organized by the steering committee of RV, and everybody is also welcome to join that meeting. Thank you.